So week number 8B, okay? So that is week of realization. We find out that the G can be written as kind of A, B, C, D. This is a compact notation widely used in robust control. So you basically say this is a realization of G, okay? G. So we talked about 4 different types. Subspaces. Only this is called minimum, okay? This is called minimum. So for this minimum, we had a principle about how to do this minimum realization. Basically, you need to get the controllable and observable both fully ranked, and then you will be able to get the minimum. But the minimum, there are so many minimum realizations there. Last lecture, we talked about Hankel norm and Markov parameter-based, Hankel norm, Markov parameter-based minimization, minimum realization. It turns out that there is a very detailed example in the textbook that you can definitely follow it. But from my perspective, I never really used that realization approach. So let's do a very quick review about what we have. So this is what we learned last time regarding Lorentz series Hankel matrix. So remember, this is a symmetric. Okay, this is a symmetric order Hankel matrix. Then from the Hankel parameter Hankel matrix, and we can have a minimal realization algorithm. Okay. So that's basically what we went through last time. Okay. Last time. So then we assume that everything is done. I want to insert something called, because we already have a Hankel matrix. So it's not so far away from Hankel norm. Okay, we are going to learn about minimum realization. We'll talk about balanced realization based model reduction. Okay. So although you have non-minimum, so not minimum description of your states, okay, that resulted you have some subspaces not controllable, not observable, so that's why you need to have a minimum realization. But among the minimum realization, suppose you already did this one. Suppose in the end, this is your state dimension n. But in many cases, the n is still very big. It's too big. Okay. So, assuming that for all the states, all of them are both controllable and observable. But there are some of them are more controllable, more observable. Some of them are less observable, less. So can I do some truncation of weakly controllable and weakly observable states, truncation of the states. That is the idea of model reduction. That means I ignore those weak states. Okay? I keep those more important states. Then the system is still a good representation of the reality. So this everything is a model of a reality, okay? Reality or real world, okay? Real world. That's why in the real world, the model of that one, usually you need infinitely many states to fully describe it. Say for example, usually in the real world, you have a PDE, okay? So it's distributed parameter. So then you put it here, it's actually a lumped parameter. Lumped parameter. This is distributed parameter. D parameter system, DPS, LPS is lumped parameter systems. Okay, lumped parameter systems. So here we have infinite many states must be used to fully describe the real world system. Say for example, the temperature of the room. Okay, it actually follows a diffusion equation. Okay, diffusion equation. But in the real world, it's a diffusion equation. Okay, diffusion. This is already infinite dimensional system, but then we use approximation to k over Ts plus 1 E minus Ls. This type of first order positive delay approximation to that. So you can see the heat up is like this. So the reaction curve, so it's similar. Okay? Similar. Don't have to solve PDEs. So this is called lumped parameter thinking. This is distributed parameter thinking. This is infinite many states. This lumped parameter, if you don't do well, you end up with very big n. Very big n. So we want to squeeze the n further, although it's both controllable and observable. So that's called model reduction. Okay, you don't need this high order. You can use a lower order system. So remember that all the models are wrong. All models are wrong. Some of them are useful, therefore we need to ask. We do modeling for what? Okay? We do modeling for what? So that's the question we have to ask. So you don't have to use unnecessarily high order, okay? So that's the topic for today. We are going to talk about balanced model reduction. Before that, let me remind you that our whole semester linear multivariable control here is only kind of 30 slides here summarized. So I uploaded the slides so you have a look. You will feel like, wow, now I know the language. I see, oh, it's summarized in the controllability, observability, interconnections, realizations. Power and zeros, you can put it down. But not able to do it. It's too much geometric theory inside like Macmillan form. We're not going to cover maybe until the later stage of time. I have another idea later on. Instead of I talk about pose and zeros, Macmillan forms for you, everybody. So I hope we have 30 minutes each overview of different topics. I call it focused independent study. Based on your best interest, you pick up a topic, give a tutorial. Okay? Say for example, you have periodic system. So there is a system like this. Okay? So x dot t is a x t. So what if I have a t plus capital T is a t? So it's periodic. Okay. Okay. So that kind of topic is a specialized topic we can consider to focus and give us tutorial about what about this. Okay. But otherwise, everything will be covered, like stability, stabilizability, detectability, observer design, and so on and so forth. So So this deck of slides I'll share with you. You can take a look, see how much you still don't know yet. Okay? But majority of them we already covered. Okay? So balanced model reduction. You can see we only have not so many slides, but really this is very dense. Okay. We start by Lyapunov equations. Then talking about gradients, okay, and we have learned this thing before. We have also learned this thing before, and haven't talked about this. So balanced realization is a unique realization that itself is a minimum realization, both controllable and observable. However, using balanced realization, you can claim that that realization is unique, is equally controllable and observable. Very beautiful. So then talking about how you compute with that using MATLAB. So this deck of slides will contain many of the MATLAB commands. So you know that you want to solve something using MATLAB. My wisdom is there's a 99.99% of opportunity that others already prepared the solution for you. You don't have to rewrite anything at this point. Unless your problem is new, nobody even knows. So there's not much left for you to do, to discover or to contribute. Okay, trust me. Unless you really attack on the real problem, real world, a new problem, then you have a new theory, new math. But otherwise, these are always codes. So you need to know the theory, but also you need to know the computation. So that's my advice. So you cannot say I live with equations, cannot compute. Ask MATLAB to help. So this is a very nice set of slides. So this probably will also be part of our exam questions like that. So don't ask me why. This format, X is n by n matrix, A is also n by n matrix, Q is n by n matrix, and giving A and Q, what is X? So this is, X is unknown. So this is called Lyapunov equation. So giving Q, giving A, how to solve X? Can we find an X? Okay. So that's the question. So if A stands for n by n matrix, this is a transpose. Okay. A is a LTI matrix, and itself is stable. The stable, there are something called stable. Some people say stable. Some people say Hurwitz. Okay. Hurwitz. Some people say stable or A is Hurwitz. So, in nonlinear control, when you say stable, it's actually another phrase is ignored. So, stable in the sense of Lyapunov. I'm going to elaborate this one perhaps next Monday. Okay? This next Monday, I will get started about what do we mean stability in the sense of Lyapunov. But for Hurwitz, basically when people talk about Hurwitz, is talking about LTI system, possibly SISO, and talking about all your characteristic roots living on this left half plane, okay? Left half plane means the eigenvalues of A, matrix, and its real part is less than 0. This, and for all I, okay? So then it's called Hurwitz. A matrix is Hurwitz. Or A matrix is Hurwitz. So if A is stable, then we know that there is corresponding state transition matrix like this, right? T minus tau. But here, you are going to see that is integration from 0 to infinity of e to the power a to the power of t. And you do this e to the power of t, q, and this one, and dt. And integration 0 to infinity will get this x. Isn't this beautiful? Yes, it's very beautiful. So in this case, x must be positive definite. Q must be positive definite. So if q is positive, then x is also. If q is semi-positive definite, semi-positive definite, sometimes negative definite, semi-negative definite. So PD, ND, or semi-positive definite or semi-negative definite. So in this case, if Q itself is semi-positive definite, then X is also positive definite. Some people will write A transpose X plus A XA is equal to Q, minus Q, okay? But it's the same, okay? The same. So in another thing to observe is you put this Q positive, semi-positive definite, then you put a QA as an observable pair, okay? Observable pair. If the X itself is positive definite. So this sounds like an interesting connection. We haven't seen a state space yet, but let's try to see if this is true, and we'll put this X in, what we are going to get, okay? So we have transpose in here, we have QEAT in here, so then we bring this A star in here, okay? Then QA plus this one, okay? They just bracket in here, A transpose this one, and this one A. So it is interesting to note, okay? This is a EAT. So this is keep this one unchanged. You have EAT, and this side is A. So in the end, we're going to write something like this, okay? Something like this. Okay. So this one will be infinity, put it here, and minus 0, put it here. For 0, put it here. These are all the identity metrics, so it's minus 0. Okay, so it's minus Q. For t is infinity, then because this is stable, then t infinity will be 0. Okay. Because A is a stable matrix. A is a Hurwitz. So that's why this is a minus Q. And put this Q this side. Done. Okay. Isn't this beautiful? Yep. It's beautiful. So in this case, if we so I hope you see this is just the whole differentiation, and then you do 2 parts. Okay. Do this differentiation first. Keep this QAEAT unchanged. You have A star and AEA star. Same thing is true. Keep this one unchanged, and you have this one. So yes, they are connected in such a way. Now let's assume that the E can be decomposed. The Q can be decomposed using the C star C. Okay. Doesn't matter, C is not necessarily square matrix. So C is not square, okay? Not necessarily to be square. So if X is a positive definite, that means this guy and transpose for any of the V, this one will be greater than 0. So then you can write X is in terms of this form, and you can write it in this 2-node form, okay, which is you split this Q with C star C, so you have vector times transpose times another vector, so it's a C E A T V, okay. So if this is singular, then that means there's a V inside the C to make this singular. This is also saying that if this is singular, that means everything you add another A in here is also singular. It's also 0. So in other words, you put CA not observable. Okay? And then QA is also not observable. So that's why you connect this LTI system with the Lyapunov function. So the X is n by n matrix. So this is n by n, this is n by n, this is also n by n. So everything is n by n. X, capital X is n by n matrix square. So let me repeat. So if you have a matrix A that is stable or Hurwitz, and you put this Lyapunov equation format and let Q as semi-positive definite, then you will be writing the solution X by this integral, okay, by this integral. And the X will be positive definite if Q is positive definite, okay, and semi-definite. So this is a conclusion we can see. Also from system point of view, we can see Q and A is observable pair, okay. We have shown this proof here, okay. So this is Lyapunov function. We have further conclusions here. So supposedly, I find X is a solution of this one. A is a stable matrix. Q is positive semi-definite. So then how can I know what is my eigenvalue of A? So I know that if my A, all the eigenvalues living on the left half plane, how do I know? Checking the eigenvalues of a matrix A is considered as another simple task if you compute that. Not easy, okay? So, but how can I check the real parts of the organ? All the eigenvalues are less than 0 here. Okay, how can I know without solving it? So there's a way you can, without solving the eigenvalues, by checking this Lyapunov equation. If you are giving a Q semi-positive definite, then you solve the X is positive definite, then that already implies A is a stable matrix. So that offers another way to check the stability of A, or stability of a matrix. So you just try to solve the differential algebraic equations X. So X has n by n unknowns, so you just solve this equation, matrix equations. There are very interesting algorithms to solve the matrix, giving A Q, okay, giving A Q, then you can solve X. Then you give any Q that is greater than, is a semi-positive definite, then you check whether the solution of X is positive. If yes, A is a stable matrix. X dot AX is a stable system. So is a stable if X is positive definite, and Q is also positive definite. Semi-definite, and this is also detectable. Okay. So all these conclusions are very interesting connections. From utility point of view, you can tell if A matrix is Hurwitz or stable, and you don't have to solve all the eigenvalues. This looks like a brute force approach. It's not smart enough. While this one is an alternative way, it's a smart way, the authentic way of doing that. Okay, so if you want the proof, here is a short few lines of proof. So we say that if lambda is an eigenvalue and is a corresponding eigenvector, so then you have this one. So you do what they call quadratic form. Okay, you have vector times a matrix, square matrix, and have a transverse matrix. So this is a quadratic form. Okay, so this is a scalar. Okay, this is a scalar. This is also a scalar. Okay, this scalar cannot be negative. It's called quadratic form. It could be 0. If it is 0, that means the Q is not positive definite. Okay, If it is semi-definite, this could be 0. Okay? So then we'll just say that. So now we say that this is 0. I do x transpose v transpose v. So both sides. So this is still 0, but this side will be this. So these are two scalars add together. But applying this v transpose a transpose equals actually lambda complex conjugate and v complex conjugate. Okay. Then you add this one, v, so still have this one, and you have this one. Okay. So because x v transpose x av is av is lambda v, so you have lambda. Okay, then you can do a complex conjugate. Then you will get this lambda star v star is v star a star. Okay, so you end up with this one, and you can write this one. Be careful. You have a complex conjugate plus the complex number is. This will give you the real part, 2 times the real part of the lambda. Okay, so this one I really remind you. So you have z is x plus iy, and z bar, not z bar. Let's say this star. This star is x minus iy. Okay, so then z plus z is 2x, and x is 2 real part of the z. Okay, so this is what we're doing. So lambda. So why we have this star here? Star here is the same thing, complex conjugate. In case you have a z1, z2, zn, you have a vector in here, and you do star here. Basically, you have transpose of z1, z2, z3, and zn. So you write it's a transpose of that, but however, you still need to make every element a bar in here. Let me do bar. For scalar, you have bar and bar. Yeah. So this star actually is like a transpose and then bar. Okay. It's a complex conjugate. So this is called conjugate. Okay. Complex conjugate. Okay, let's move. So we arrived at here. What we want to do is saying that because this is this is positive, this is all positive, and this is not negative. So if I remove this guy out, this is non-zero. Okay, at least above 0. Then this guy will be greater than what's left. Okay, so this is true. So this is what's left in here. So Q is positive semi-definite. So in this case, because 0 greater than this, that means the real part has to be less than or equals to 0. So on the left half plane. But on the other hand, if lambda is 0, that means they live on the imaginary axis. So then you have QV is 0 and AV is lambda V. So if you do the PBS test, then in this case, you cannot detect. So in other words, if I add something detectable as a condition, that means we should eliminate this case. So nothing will be on the imaginary axis. Okay? Make sense? So be careful. So that's why this here we need another condition to add in here. Make Q, comma A observable. Okay? Yeah, here they add a QA detectable. Okay, so we talked about the Ableton function and its connection to LTI system. And so now let's talk about gradients. Looks like gradients this time is pronunciation is correct. Single M. Okay. So we assume we have Gramian, and I hate this, but we have tolerated that. So remember we used the Q previously for that. Now we got another Q. So that Q is very different, okay? So assuming this is called observability, Gramian is Q, while controllability is P, okay? P and Q, so please don't get confused. Nothing to do with previous Q, okay? Just here we just differentiate. Controllability, Gramian is P, observable Gramian is Q, and so you have a LTI system, you have CA pair AX plus BU, Y is a CX. So if CA should be observable, if it is observable, then how you can check observability? You have rank condition you did before. Now, you say that, hey, if I insert, okay, my observability Gramian, that is positive definite, okay, positive definite, then the A transpose Q, QA, this is the out of equation, and they put C transpose C in here, and this whole thing, okay, if and only, okay, so the observability becomes whether Gramian can solve the Lyapunov equation like this. Putting C transpose, you can C transpose C and A transpose Q and QA. This is the Lyapunov equation. So similarly, you have another thing called, so this is observability. Here is a controllability. If and only if we have controllability Gramian P solves the Lyapunov equation with the B transpose here. This is AX plus XA transpose. So a little bit different, right? So the AP is here, but remember A transpose Q is this side. Here is a P is this side, A transpose. Okay, so be careful. Okay, be careful. It's a little bit different. So this remark, I do know this remark. People say, hey, it's not matters whether there exists a solution or not. We're not talking about that. We are talking about it solves this equation. Okay, but it does not mean that A must be stable. Okay, but the solution you got, the P and Q may not be just Gramians defined. Okay. I think the type of G should be capital. Okay. So, okay. So controllability, observability Gramians solves the Lyapunov equation. Amazingly interestingly connected. So we're moving forward. Okay. So we have learned you have A, B, C, D. You can always do symmetric matrix. P is P transpose. No, here P again is P is nothing to do with previous P as Gramian. Okay, no, may not. Okay. So this P P1 non-singular such that you have this one curve solves the Lyapunov equation. You do partition and then this A11, B1, C1, D. This is a realization of G. Okay? So when we say A11B is controllable if A11 is stable. So that's a partition of the A matrix by doing this type of P. And how we can prove that? There is a one-page proof. Okay. So, yeah, if you insert A matrix, partition matrix in there, you are going to get Lyapunov equation in terms of A11 and P1. Okay? So because we are using P1 here, okay? So the others are just zeros. Okay? So we got this one, then we are going to write other equations. You have other blocks. Okay. B2 is 0, A21 is 0, so that part of realization is not controllable. So basically you have this A11, A2, B1, 0. So this is called A11, B1 is a controllable subspace. So basically is this part, CO and CO bar, this is controllable subspace. So we have seen this before, because we need a specific, here is a 0, here is a 0. Okay? So if P happens to be positive semi-definite or positive definite P1, then the controllable part is also stable. So then this thing is controllable. Similarly, we can have observable decomposition. We use Q in this form, solving this Laplace equation. Then you have partition like this. So this is A11, B1, C1, D1 is realization of the G. C1, A11 is observable. So that is observable decomposition. We learned this one in terms of observable form of decomposition. Okay. So here comes something interesting. Please pay attention. So that is, so you have two Gramians, controllability Gramian of the Gramian. So how we can do a balance of realization is if somehow you put P and Q, you do what? You do what they call singular value decomposition SVD to make it diagonalized like this. The P and the Q diagonalized. So let's just do. So you find a realization A, B, C. Okay. A, B, C, such that P and Q are the same, and also P and Q are diagonal, okay, diagonal. And this diagonal also having a ranked, not ranked, ordered, sigma 1 is largest here, sigma n is the smallest, all of them greater than, so this is SVD. Why we can write that? I said this could be 0, okay? Why we write that? Or we could have multiple zeros until here, right? Why we have that? It's because P and Q, they are positive semi-definite. If you do SVD, then you always have SVD, but you may have several zeros. Okay? So if you are purely definite, positive definite, so your SVD is a diagonal, it's non-zero. None of them is 0. Okay? So if we make P and Q and equals maximum singular value ordered, so then you find out A, B, C, this realization is called balanced realization. So it's not just P equals Q, but also it also must be diagonal, okay? Diagonal. So these sigmas, maximum singular values, has a special name in this case. It's called Hankel singular values. Hankel singular values. And this ABC realization such that P and Q and equals this diagonal is called internally balanced realization. So why they say internally? Why they say balanced in what? I hope you understand the balance is not in terms of observability, equally observable and controllable. I believe it's also decoupled, okay? Because this P and Q are diagonal, okay? Diagonal, decoupled, okay? So if you set Q still like the diagonal, but P is identity, okay? And Q is a sigma square, okay? The square. So this is called input normal realization. It's normalized. The input normal realization. And if you put Q is identity, that is called output normal realization. Okay? So this is just, you can understand. So you can understand. Is this a unique? Yes. This is also a unique realization. There's no other form. It must have one. So this is also a unique realization, or balanced realization. So this is all unique realization. So it's called input normal realization, output normal realization. So, and you should understand why we have this type of different unique realizations. It is for this one, three of these. It's just kind of scaling, okay? Scaling of the states. Scaling on the states. Scaling on the states. So that's why they call this is a balance. I think this is like, oh, the system, this controllability more important than observability. Depends. So in the system, how we really do this kind of balance realization, okay? So you're giving A, B, C, D, what are you going to do? So you want to compute P and Q, and how you can do it. So basically you should just go a different direction. So let's do this. So minimal realizing, balanced realization is, first you have a minimal realizing A, B, C, D. Then you do what? You do a similarity transformation. Find a T matrix. So, but how you can find a T? Basically, you need to find out sigma first. What is sigma? Sigma is SVD. Okay? So then you basically do a transformation of P of Q. Your T is constructed from here. You make a diagonal of this one to diagonal this. Diagonal this, then you can actually write in terms of sigma squared in here. But because P and Q are always can be written as R transpose R, that is positive semi-definite for sure. Positive definite actually, not semi-definite. So in other words, you will be able to partition the P in sigma 1, sigma 2, sigma 1, sigma 3. So in this diagonal and positive definite in this form, okay? So giving A, B, C, how to get P and Q, what you do is solving this one, okay? Solving this one, you have a unique solution. You don't have to do iteration. So there are a lot of functions. There's a lot of dedicated function to solve this P and Q. Once you get this one, you can decompose into a transpose format. So you get R. So then you put this R and do this, diagonalize this one to get unitary matrices, and then in the middle is sigma squared. Okay? In this sigma, if you get this unitary, and you just put how to construct the the final similarity transform is split this one by half. Okay, so then you are going to have a U. Here, this side you have R's. Then finally, you put everything. This is already shown here, so you finally get a diagonal matrix like that. So this probably is a little bit abstract, and let's see this one. So if you have an original system A, B, C, D, so you can get state space. G has a name. It's called LTI object, okay, minor. So what do? You do balance realization of G. It will give you T inverse T. That is here. T inverse T here. Okay. That's a balance realization. So. Then you're also giving a sigma. That is a diagonal matrix. Okay? Sigma is the vector of Hankel singular values, ordered from biggest to smallest. Okay? So this GB is another LTI parallel to this G is a balance realization LTI. So then you want to see what is ABCD for this GB. Basically it's here. This new ABCD, what you should do. So there's a command. A balanced, B balanced, C balanced, D balanced. I want to know what is the parameter inside here. Okay? So what you should do? Equals SS data GB. Okay? But if you get this one, how you can do GB? So it's SS ABCD, okay? That will give you a GB2. So the GB1 and the GB2 is the same. It's called LTI object. So giving ABC how to construct the LTI object, and giving object how you extract the ABCD. That's called SS data. Okay, SS data. Go and play it. So here is the question about. So I have ordered Hankel norm in here. So that Hankel norm, Hankel singular values, sigma 1. So let's try to decide the bottom R. The first R I'm going to keep. Okay, the bottom n minus R I'm going to delete. So sigma 1 to sigma R, they are just big enough. I want to keep. I want to kill the bottom ones because they are so close to 0. They're very small compared, because like order of magnitude difference to that one. So in other words, the in and out coupling, these things are less important compared to other states. After we did this balanced realization, we can see that here. Okay? So suppose we do that cancellation. It's called truncation. Those less controllable, less observable states. We don't need them. So just throw away. That's the way to do model reduction. And that model reduction has very good physical insights about what you really throw away and how much you lose. Okay, so that is a very interesting topic about bounds. So of the error. So you know that you have a G of S, A, B, C, D. Then you do truncate the R plus 1 until n those sigma Hankel singular values. You cancel that, and this is called G reduced model. Okay? So, as I told you, all models are wrong, but some of them useful because this is more useful because it's simpler. Okay? Say for example, you have 1,000 slides, have 1,000 states, but here I probably only do 6. Okay? So it will be easy. But we really want to understand what's the difference between this. And especially when I put the bound on this. The worst case, what I have lost, accuracy. And whether this accuracy will be able to give me trouble. And I can prove rigorously how much trouble I'm going to get. If that's so, then everything will be beautiful, right? Life is better if we do know the loss. So here is something we need to discuss. Listen carefully about the bounds of the function of the norm. So here is very beautiful result. This very beautiful result. I feel this is the most beautiful part that we should know. So then you have ABC. This is already a balanced realization. So here, this is already a balanced realization of A, B, C, D here, A, B, C here, you don't have D. Now, yes, I know that I have a sigma in here, S1, S2, Sn. So why I have S1 in here? It's multiplicity, right? You could have a multiplicity, right? Yes, yeah, you could. But don't worry about it, it's a block diagonal, okay? But we order this in such a way, okay? So then we know that this is P, this is also Q, so this equals P equals Q. So we've got P in here, this is Q, this is P in here, AP and PA transfers to B transfers to 0. So these two diagonal functions should be true. So this is true, and interestingly, and this is the original system, balanced realized, so we haven't truncated yet, okay? And I know that the infinite norm of this guy, G, the infinite norm. Okay, well, what is the infinite norm? So I'll tell you in a minute. So I know the size of it. It is definitely greater than the largest singular value, but it's also definitely smaller than 2 times of all the singular values added together. And this one is all in between. You can put in the impulse response norm into it like that. While this impulse response is CEATB, is the inverse transfer function of G. So let me give you a background material about infinite norm. Okay, so. Okay, so I'm going to help you to understand what's this. Okay, what's this? In fact, computing this one is going to be quite difficult. Okay, quite difficult. So, but from SISO point of view, okay, so you have something here. So is a G of S SISO. So then you can do a body plot. Okay, you can do body plot. So this is omega. This is magnitude. Okay, magnitude. So you find out something like this. So this is the peak magnitude. So basically, is max omega and magnitude of J omega. Okay, is defined as infinite norm. Okay, so it's a peak value. Okay, peak value. This is a SISO case. However, you have a Gij in here. So how we define this one? This is a matrix. Okay, this is a matrix. Okay, it's very difficult to do that. So what you do is you still do this max omega. Okay, and what you do is a sigma bar of G omega, giving omega. Okay, you have sigma bar of that. Okay, maximum singular value. Okay, maximum. This is the maximum singular value of this matrix. Giving omega, you have a matrix, so maximum singular value of that. So for this, all the maximum singular value of that, you do maximum one. It is considered as this definition. So probably this is easier to understand. But there is also time domain H infinity interpretation based on A, B, C, D. That is very involved. So it's H infinity control. There's a very long theory about it. But for this one, you understand this is like, always remember it's peak norm, meaning it's worst case is this size. Worst case. Okay, worst case. There's a worst case gain. Okay, worst case gain. So if you remember this phrase, it's fine. Worst case again. Okay. If you have two norms, then that is just add all the energy together. You don't know where is your peak. So infinite norm is basically worst case norm. Okay, worst case norm. Two norm is an energy. Okay, it's an energy. So total energy should be less than something. That's performance. Okay, so computing giving matrix transfer function infinite norm is very involved actually. Very involved. You need to scan all of the MEMA, right? So scan all of it. So usually it's hard. However, I know based on my Hankel norm, I can bracket it. So I know the bottom line is sigma 1, at least sigma 1, then worst case is this. In the middle, this is impulse response function. So kind of nice. This can be proving, and probably don't want to go through that proof. When you have A, B, C, D, then you want to get proof of this. So basically, we are trying to get, let me see where we are. So what is Z? Z is the impulse response, giving input, giving initial state, and then response due to that initial state will be like this. It's just a response to the initial condition. Then this Z integration square become this, because this one we know is following a sigma, we know the sigma. Therefore, and we know that this is true. And oh yeah, I forgot to mention here. That's why we say worst case. Okay, this one says worst case. Do you know that? Suprema means the largest. Okay, suprema is the largest. The smallest, the largest. Okay. Suprema means you have largest, but the smallest, largest. You know, suprema. Okay. So this is suprema. So this is input energy. This is output energy. So that's 2 norm divided by 2 norm is a concept of gain. Okay, in and out. So it's y divided by u. Okay, it's a gain. So this is a gain. So this is highest gain. It's the same concept I'm doing here, or here. Okay, the same idea. I'm doing here, but writing in a different way. Okay. Okay. So this is a worst case gain. Okay. So you can write in different ways. You can, input energy is here, output energy is here. Then in and out commute in terms of sigma. Then you got sigma 1 left, because you want to choose the highest. Okay. So that's all. But on the other hand, G of S is a Laplace transform of the impulse response G. So then this one can be written as suprema of this one. Then it's less than this one. Of course, less than this one. So that. So another page of proof. We can skip that. Well, here comes this question. So I cancel. So I keep this GR as my reduced model. In original model is n. Now after reduction I have r less than n, and I truncated n minus r. So this is my truncated one. So then I hope I understand. What is the g minus gr? Okay, so that I make sure that my degree of the gr is already less than or equals to r. Okay. So this is called additive model reduction. So then what's the model reduction, and what's the beautiful side here? So after reduction, you have G is the original one. So you have original system like this. Then this one has a balanced realization like this. Then in this case, you have sigma 1, sigma 2. So this is sigma 1 to sigma r, sigma 2 r plus 1 to n. So then you rank this thing we have seen before. So then we are going to do a truncation. The GR has A11, this was left. So what's the most beautiful thing is, I love it because I know it. Original model minus my reduced model, okay? Its worst case size is less than this. This is beautiful because I do know what's my upper bound of my uncertainties I introduced when I truncate and I use the symbol. So I use the simplified model. I know how much uncertainty I brought in this size, okay? This size. And if I can design a controller that can tolerate this size, be robust to that, then done. So I did a control using a simplified model, yet the same robust. This is very beautiful, right? Very beautiful. And this can be proving, okay? I'm not going to go through this. But you should understand, this is the beautiful result, okay? And it can be proven rigorously. And this is G infinity, okay? G infinity is, do you know that what is G infinity? G infinity is Markovan parameters G0, right? Okay. GS can do a Lorentz series expansion G1, G0 plus G1, 1/s plus G1, G2, 1/s or 2. So if you do that, it's only have G0 left. Well, G0 usually is linked to what? D. Okay, D. So usually D is 0. In other words, the GS worst case norm is less than 2 of all the Hankel norms added together. This is another very beautiful thing, okay? And if we only truncate the last term, then the truncation area is not equals, it's exactly equal, okay? Not less than equals, it's exactly equal to sigma n, okay? This is also beautiful, okay? This is very beautiful. So you cancel the least one, then you know exactly this is the exact bound. Okay. So how to prove all these things? Probably we should not go through them. Additive reduction. But there is, I want to show you there's another part, it's called multiplicative. So the upper bound, so this is about additive. So I have 4 pages of proof in here, okay? But original paper was written by Case Glover in the International Journal of Control. Probably it's 1990, I forgot. Okay? It's called a Hankel norm of a linear system. And this paper is the longest paper I have read. It's 90 plus pages. Longest control papers I have ever read. But maybe this still keeps the record. Okay? That's why he received lots of respect. So he's thoroughly understand about this Hankel norm and balanced model truncation. So these are modern results. You guys should know. So let me show you, answer the questions, the tightness of bonds. Okay. So how tight is the bond? Okay. How tight is the bond? So I do truncation. We'll see how tight it is. Okay. So basically we use example to see. Probably you should know what is this one. This is by, you have a Saiso transfer function. then you have you have pole and zeros in the product form. Then you do the partial fraction expansion, okay, PFE, okay, PFE. So I'm not sure you understand what I'm saying here. Let me give you an example. Okay. So you have a transfer function, x plus 1, x plus 2, s plus 4, s plus 3. So I want you to write this on k1, s plus 2 plus k2, s plus 4 plus k3, s plus 3. So do you know how to do that? And immediately, if you don't, you need to learn now. So this is called PFE, partial fraction expansion by immediately solving what is K1. So K1 do a cover up and plug in. So this one I cover up this term, plug in minus 2. So this is minus 1, this is plus 2, this is 1. So this one is 0.5. So for this one, I cover s plus 4 and plug in minus 4. This is gives minus 2, minus 1, minus 3. So this is minus 1.5. Oh, no, 1.5, minus 1.5. This is minus, right? So minus 2 in here, 2, 1, minus, yeah, it's minus. All about K3 is cover up this one and plug in 3, this is 1, this is minus 1. Minus 3 here is minus 2, so that one will give me positive 2, right? So this is my partial fraction expansion using the Coupe rule I just explained in my undergraduate course. So then you are going to have a form like this. You're going to have a form like this, sigma of this thing, okay? Giving a transfer function, you will be able to do that immediately, like what I did. So this one can write very easy. Let's say these are different, so you can write this controllable and observable form like that. So we don't have a case of translation of modes, right? So we have 0 here, so everything greater than 0. Then in this case, your PQ can be written in an analytical form like that. And G infinity in this case is G0, when everything is 0, so you have together like that. This is exactly 2 times trace P, which is 2 times of sigma I. So amazing, right? So this is verified. It's verified, right? So the whole thing is, this one is G0, this is, so remember G0 is what? G0 is called DC gain, direct current, when omega is 0. Direct current. Omega is 0. So DC gain, imply of the gain. It's like that. Okay? So let me go back. So remember, this G of S infinite norm is G0 and is 2 all the sigma added together. So let me go back and just check out the result. This one is here. Remember, G infinity is 0. G infinity is 0 in our case. D is 0. Okay? So in this case, you can see the Sasso case, this is not less than is equal. So that means our bound is, in the Sasso case, this bound is tight. Tight, it's very tight. So tightness, we're talking about tightness. So this shows you this is really tight. Okay? It's not like exaggerated. So the worst case is less than infinity, right? So it's meaningless. So you can also try to use Hankel single norm close to each other. So you have Hankel singular values given by this these two things, they are so close, okay? They're very, very close, very, very close. So these are the bounds of this. So R is 0, you don't truncate anything. Yeah, no. Sorry. If I keep all of them, R is 3, right? So I keep everything. I didn't lose anything.
It's 0.
Huh?
0
is?
It's 0 because 2. That's maximum
No, this 0 means I truncate everybody. Only leave 1. So it's a 4x4 system. I have 4 sigma. Okay? So when R is 1, I truncate 2, 3, 4. When I 2, I truncate 3, 4. And 3, I truncate the last one. And 0, I don't truncate anything. I don't have anything. I cannot truncate 4, right? So I didn't truncate anything, right? Truncate 0. Kind of. So this is the original system I did. Then this is 1, truncate 1. You keep 1, truncate 3. You keep 0 means you keep all. Something like that. R is the one from 1 to R you keep. So I'm not sure it's very confusing. So yeah, if 1, 2, 3, 4. But anyway, that is R3 is kept. 4 is 4 is truncated. So truncated 4, truncated 3 and 4, truncate 2, 3, 4, and you don't truncate, right? Right? So then you will check the original system is here. Let me do that. They just gave some examples, give numbers. So these are all almost like 1. So then you get. So you can see what is the best R. You can draw that curve to see where you should cancel, truncate. Yeah, you definitely will have an idea. Okay. So I think we are done. But in real world, you sometimes may say, "Oh, I do have some frequency domain insights. I know that I want to keep more frequency than high frequency. So in this case, you add some weighting filters, W's. These are the filters. So you put frequency weighted, it's called frequency weighted, then you do the truncation. So how you do that? So there are systematic ways to do it. So you do a realization of this, and then you do the state space realization, you do this Lyapunov function, you do this weighted gradients P and Q in the new weighted system. You do the same procedure in the end, you can do that. So good news is you do have a command, it's called reduce, okay? Using input weighting filter, output weighting filter, then give an option, and you do this reduced mode, so that you can add those filter thing. Oh yeah, here is, we can finish after this, okay? So the basic idea, remember, we did reduced order is G plus delta, right? So that's called, you have G, you have GR, and there's difference between them, so I want to know the size of the difference. But in many cases, they don't care about the difference. They care about the relative. Like you have a gain, original system, you multiply something like that, I plus delta. So this is called model reduction, relative reduction. Okay, relative. You don't have. This is called additive. This is called relative. Okay, so then you have a transfer function here, but this is not really hard, and this is equivalent to a frequency weighted, like you put G inverse as a weight. So you can solve as the WO/WI format, like this one. This is I, then this is G inverse. Done. So it's actually easy. And last slide is this. So this is called relative. So relative model reduction. So this is the command to get you the reduced model. Okay, we'll give reduction information in this object, and of course the relative reduction, the size can be estimated by this one. All these materials are contained, discussed in since the work of Keith Goldberg, is a Cambridge University professor in control. I met him several times and we never talked. He's a giant in our field, consumer. That's all.